Hello everyone, let's continue our discussion on the LTE, more on the LTE and finally the 5G, onto the 5G. Now let's start with the data plane and control plane separation. Okay, so in 4G, the control plane has new protocol for mobility management and then security and authentications. Okay, we'll talk about this later, and especially to set up the tunneling. All the tunneling is part of the data plane, but then setting up tunneling is set up by the control plane. Okay, so and then and in data plane, new protocols at the link and physical layers, of course, because it's not only the wireless between the wired and wireless networks technology, but also between the LTE, 4G, and the 3G, they have different physical layer technologies, and also at the link layers, as we will discuss later. And then it is using the tunneling extensively to facilitate the mobility. Just to give you an idea, the tunneling is the mechanism or the technique that is also used in VPN, and basically in VPN, let's say if you are using VPN to connect to the campus network, or let's say a worker in one company, when they have to work from home, or let's say when they're traveling abroad in foreign countries, they have to work by using the VPN. So basically what happens is, the other side of the, let's say, the servers in which the workers are connected to, think that the workers are working from the company's networks, although it's not. So that's really the function of VPN, or eternal links. So basically, the other side of the other side of the other parties in which you are communicating to, doesn't really do not have to know where your exact location is. Okay, so this will be handled by the core networks. Okay. Okay, so now let's have a look at the first hop, the link layer protocols. In we have the same stack, application, transport, IP, and then in the link layers, one, two, three, four, five, yeah. And in the link layer, there are several sub layers. The first one is packet data convergence. It has several functions. The first one is header compression. This header compression is very important, especially in the wireless, because we want to save bandwidth, right? Because if we are, the header is not compressed, then there is a big overhead, and then we are wasting a lot of bandwidth, and also to save the power. Okay, sending bigger data, uses more power than a small data, and also encryption, right? And then there is a radio link controller. Its the function is for the fragmentation and reassembly, and then reliable data transfer. So this is like in TCP, where it can do retransmission if the packet is lost. But then this is done at between the base station and the UE, okay, user equipments. Okay, while in TCP is end to end. So it doesn't have. I mean, the retransmission is faster, much faster than the TCP, because it doesn't have to wait. After several for more times. Okay, to wait from end to end communication. Okay, so this the and here the retransmission is faster. There's also fragmentation assembly, which is also done in the IP version 4. But then this is because basically there are different maximum transfer unit, right? MTU. So the packets needs to be fragmented, and at the end, when it arrives at the destination, it has to be reassembly. Okay, and finally, the medium access. It is for requesting and use of radio transmission slots, and this is highly related with the access technology, which we will talk in the next slide. Okay, so in LTE, there are two different medium access protocols or medium access techniques. Okay, for downstream channel, or from the base station to the user equipment, it is using OFDMA, or orthogonal frequency diffusion multiple access. And for the upstream, from the user equipment to the base station is using the SC-FDMA or single carrier FDMA. All right, so let's start with the OFDMA. So, well, OFDMA is basically it's totally different technology than what we have combined FDMA and TDMA that we have seen in the GSM. But okay, so basically in combined FDMA, TDMA, and GSM, in one base station is only using one frequency band. Okay, so the FDMA is between multiple cells. Okay, but in LTE, FDMA. By the way, FDMA is also used in Wi-Fi 6. Okay, the latest version of Wi-Fi. So in FDMA, one base station can have several. It is called now a subcarrier, okay, or sub-frequency band. But then, different subcarriers, they are orthogonal to each other, so there is no interference between subcarriers. And this is very important to define the bandwidth of subcarriers and space between subcarriers and so on. So it's there's this is the whole different course, just to learn about the FDM and then the FDMA. Okay, so yeah, the orthogonality it minimizes the interference between the subcarriers. There's still some interference, but it's very small. Okay, and then there's some techniques to avoid it or to prevent that to happen. And the upstream, it is using the SC-FDMA. Well, I don't really know what's the difference between the SC-FDMA and the basic FDMA. But what I can tell you is that basically when the user wants to send data to the base station, it is using different frequency, okay, with the other users. Okay, so that's the basic principle of the FDMA. Okay, now with this OFDMA, basically each mobile device is allocated 2 or more 1.5 millisecond time slots and over 12 frequencies. So basically now we can have something like a grid. Okay, so let's say if we are having this grid, so let's say this is time and this is frequency. So we have this 12, okay, 12 frequency, and the time slots, the space of one time slot is 1.5. And every user can have one or more than one time slot. So basically, the allocation in the LTE or FDMA is more flexible. The scheduling is not standardized; it's up to operator. So it is really like the allocation or scheduling algorithms that has to be utilized. So it can have more capacity in FDMA or in LTE. So basically, 100 megabit per second per device is possible. I don't know what's the calculation, what's the how this calculation can be done. So perhaps it can be like only one user is occupying the whole, the whole chunks of this OFDMA slots. All right, now let's move on to the packet core. As we have seen before, it's the LTE is using a lot of tunneling. So the tunneling is done, let's say, from the base station. Okay, so the first hop, we have covered the first hop from the user terminal, user equipment to the base station. And now from the base station to the serving gateway, it is using a tunneling. Okay, so the protocol used in tunneling it's called the GPRS tunneling protocol, or GTP. And since it is it's working over the UDP, so it is called the GTPU. Okay, so GTPU inside the UDP datagram to the serving gateway. All right, so this as we have said before, serving gateway is just it can be like any routers before reaching the packet network gateway, or PDN gateway, or P gateway. And then this serving gateway tunnels the datagrams to the P gateway. Let's say this is not illustrated here, but let's say we can have the continuation here to the P gateway, and then this is done to support the mobility. Okay, so only tunneling endpoints change when mobile user moves. So basically, like let's say the user moves to other base stations. Okay, let's say this is the new base station. Then only the endpoints is changed. Okay, so before it was from this base station, now it is coming from this base station. Okay, so the tunnel is here. And as I said before, like when we are using VPN, the the other end doesn't have to know our location, where our location is, or in which base station we are connected to. Okay, so it it is up to the core networks in LTE to send it, and this is handled by the tunneling. Okay, so the tunneling knows, okay, because the tunnel is already created, so the packets data that is sent to the end user is already is already known, okay, by using the tunnel. Okay, now in data plane, how the user equipment associated with the base station is the base station broadcasts primary sync signal every 5 milliseconds on all frequencies. Okay, so on all the sub carriers frequency. And BS for multiple carriers may be broadcasting sync signals. Okay, so multiple carriers means like different, telco operators. Okay, so basically the mobile can receive different signals from different carriers. Okay, and then mobile finds the primary sync signals, then locates the second sync signals on this frequency. So okay, so it first finds this primary sync signal and then the second sync signals. Okay, and then after that, the mobile finds info broadcast by the base station channel bandwidth configuration, and then the base station cellular carrier info. So all this information is provided by this sync signals. And mobile also may also get info from multiple base stations and multiple cellular networks. Okay, it because like there can be adjacent base stations, or even from different telco operators. And if we want, we can connect to the other networks. Okay, but then of course the preference is to the home carrier. Okay, but then this is very this is this is possible when we are traveling to other countries, where we can have several options to connect to different sub carriers. Okay, that's not separate, but different telco operators. Okay, after that, there is still some steps to be done. For example, authentications between from device to network and also device, then establishing states and set up the data planes. Data plane meaning like this tunneling and so on and so forth. And the LTE also has sleep modes similar to Wi-Fi and Bluetooth to conserve the battery. It has two types of sleep modes: light sleep after 100 milliseconds of inactivity, and it would wake up periodically every 100 milliseconds to check for downstream transmissions. If there is no transmission, then it again go to sleep, or it can also go to deep sleep after 5 to 10 milliseconds of inactivity. And when the user moves or the mobile equipment change cells while deep sleeping, then it needs to reestablish the association with the new base stations. All right, now when we look at this, 4G networks, we can consider this as the global cellular networks, the part of the global IP networks, right? Of network of IP networks. Okay, because now since the 4G, we introduced the all IP networks in 4G, so we can consider this 4G network as the same as the ISP, right? So the all IP, the carriers interconnect with each other and public internet at the exchange points. It could be like inter-carrier IPX, or like the in I don't remember IP exchange or internet exchange point, something like that. But then this is only works for the 4G networks and above, let's say 5G. In legacy 2G and 3G, which is not all IP, then this is handled otherwise. Okay. Okay, now in 4G, or it's not just 4G, but then especially in 4G, there is this home network HSS. Okay, the SIM card is also used in 2G and 3G. Okay, to add global identify info in home networks. So this information is stored in the home HSS, home subscriber server, this identifies and surface info while in home networks, okay, or when it is roaming. So the information about the service that is let's say it is entitled to, because different types of user entitled to different types of services, for example, and different types of subscribers and so on and so forth. And when it is going to the when roaming to the visited networks, then the home SSS has to know in which networks it is currently now the user equipment. So all this information it should be registered in the home SSS. All right, now onto the 5G. The goal is to increase 10 times in the peak bit rate. If it was 100 megabit per second in 4G, then the target is up to some gigabit per second in the 5G, and then 10 times decrease in latency. Well, we don't have what is the exact number of the latency in 4G. So basically, it even decreased to 10 times in latency because it wants to accommodate more types of services, like for example, real-time IoT services and so on and so forth. And then 100 times increase in traffic capacity over the 4G. So basically, it wants to accommodate more types of traffic. Like I think the killer ones is the IoT, and then in future there will be now there's development of self-driving cars, and then it really use extensive networks cell networks extensively, right? Because it needs to communicate with the internet, and when it changes the cells, it has to change the association with the base stations and so on and so forth. So and then the decision has to be taken in maybe some few milliseconds or maybe in nanoseconds. So the latency has to be very latency is very critical, and the traffic capacity is becomes very big, because the communication will be maybe very demanding when we have the self-driving cars or other types of IoT services. And also in the radio technology or the physical layers, it is using new radio. First, it uses two frequency bands. First frequency band is from the 450 megahertz to up to 6 gigahertz. So this frequency was just one band is very big, very large coverage. It's like let's say five comma something gigahertz just for one band. Okay, and then the other frequency is from 24 gigahertz up to 52 gigahertz. It is very high, or it's called ultra high frequency. I don't know the exact naming for this. USF is the ultra high frequency is for the TV stations, right? But this is very high frequency. Okay, or it's called millimeter wave frequencies. Why millimeter wave? Because the wavelength of the let's say if we are talking about the um, um, electromagnetic signals, okay, there is a wavelength and frequency and also periods. Okay, so the wavelength is inversely proportional to the frequency. Okay, so the higher the frequency, then the wavelength becomes smaller. Okay, so yeah, this of course this has some implications with the distance, as we will discuss later. Okay, because the wavelength is becomes very short. Okay, and it's all not backward compatible with 4G, because the 4G uses different frequency bands, first of all, and it may also use different access technology. Okay, and it utilizes MIMO is also already utilized in the 4G, but then I think in 5G I heard that there is a term called the massive MIMO. Okay, so the MIMO, let's say when we look at this Wi-Fi 6, it is up to 8 times 8, right? So I don't know in massive MIMO in 5G, maybe it's up to some dozens of antennas or maybe hundreds of antennas. Okay, Now about the millimeter wave frequencies, it is much higher data rates but over shorter distances. Okay, because the wavelength is very short. It's shorter than the lower frequency here. So the implication is that we need to deploy a smaller cells. It is called the picocells, where the cell diameter is maximum 100 meters. Okay, 10 to 100 meters diameters. Okay, so I don't think 100 meter is already is quite large actually for the wireless. So then this requires massive and dense deployment for new base stations is required. Okay, so I think that's it for the wireless and cellular networks. We'll move on in the next discussion about the mobility in the next video. Okay, so see you again in the next video. Bye bye.